Should I speak into the mic or?
No. The sound is all around. You might also hear people speaking from
Okay.
the voice of
God is correct, yeah.
Sound's coming. Oh, there you go. Okay, well, we're very happy to have Isaac Kim from UC Davis. He agreed to give us a bit of a warm-up overview of this Entanglement Bootstrap program that he's been working on, and warned that we're not all QI people, so thanks for being flexible.
You told me that today.
Yeah.
Before I prepare the slides. Okay. Yeah. I guess we start.
Yeah, go for it. Thanks.
All right. Thanks everyone for coming. So my name is Isaac Kim, and I was asked to give sort of an overview to talk about this program that I've been working on with my collaborators. Some of them are here in the slides, and we are calling this program as Entanglement Bootstrap. So what is this program about? So to be clear, the physical system that we want to study using this approach is a quantum many-body system. So what I'm thinking is like a lattice, locally interacting like lattice Hamiltonian, like in 2D or 3D. So oftentimes you can write down an explicit Hamiltonian like this. But of course, actually solving the ground state problem with this Hamiltonian is in general a difficult problem. And okay, the size is a bit strange.
I think look at before.
I think it works now. Okay. So the main goal that ultimately we want to achieve in this program is basically twofold. One is to find a complete set of topological invariants that characterize 2D or let's say 3D gap ground states. By topological invariants, I mean something that remains invariant under adiabatic evolution that doesn't close the energy gap. And by complete, I mean something such that if you two phases are equivalent to each other, if these complete set of topological invariants coincide with each other, which is obviously going to be a little bit difficult, but that's the goal. And the second goal is to come up with an efficient method to basically simulate these systems classically. So given a microscopic Hamiltonian, we like to be able to have some general purpose polynomial time algorithm for approximating its ground state energy or its ground state representation. So that's the big goal. And the main theme of this talk would be primarily what we call as area law. So that is an expression for the entanglement entropy. Inside the parentheses, that should really be the row trace of minus rho A log rho A, where rho A is the reduced density matrix of a certain subsystem of a large quantum many-body system. So there are many entanglement measures, but the entropy measure the entanglement measure that we're going to use in this talk is going to be primarily that thing, which is von Neumann entropy. And what has been noted before is that if we look at the entanglement properties of these many-body systems, you often have an amount of entanglement that is far less than what you would naively expect. So what I mean by that is that if you consider a uniform measure in the space of pure states and compute the average entanglement entropy, typically you're going to get the volume law. But in many physical ground states of interest, you often find that the entropy is upper bounded by the area. So there are some notable examples, but the key point is that if we sort of imagine having a space of all possible quantum states in the blue box, the set of like physical states that naturally appear at low energy will constitute a very small corner of this set. And our goal is to identify the specific structure that these physical states have to solve the problems that I mentioned in the previous slide. So there's a well-known success story. It's a 1D system. I think it's fair to say that this problem is completely solved at this point, in a sense that you have nice solvable models, you have an efficient numerical method, and now you have actually a complete classification of your gap ground states, whether you have symmetry or not. And the main lesson, the main insight that people have gained from this 1D systems is that in these systems, you can actually rigorously show that the entanglement is upper bounded by a constant independent of the system size if you cut the system into two pieces. And that allows us to say a lot of things very concretely. So for example, Hastings showed that as a byproduct of showing that the area is bounded by the entanglement is bounded by a constant, he showed that the ground state can be well approximated by certain ansatz called matrix product state. And this is really the basis behind the efficient numerical algorithm and also the classification. So people have been thinking about ways to generalize this line of reasoning to higher dimensions. It's kind of a natural thing to do. But so you might be a little bit surprised by this, but actually, let's say if you have 2D gap systems, you would expect that obviously the area law would be true. But actually, like if you start with the lattice model, this is like not known. So this is a hard problem, but the more serious problem is that you might think that, oh, like if you have area law, then maybe that means that you don't have too much entanglement in the ground state. So maybe that means that there's some generalization of matrix product state, which would very accurately approximate these like 2D gap ground states. But it turns out that this is actually not true. So what these folks showed was that if you consider a family of states which satisfies the area law, that set is like already too large, so that no like 2D tensor networks, which is like a generalization of matrix product state, can actually cover that entire state. So in order to make progress, it looks like simply proving area law is not enough, and even like simply assuming area law is not enough. You need to make some extra assumptions, or you need to show something stronger. And the entanglement bootstrap approach is trying to make one attempt to make progress to this problem. And our starting point is very simple. So one of the authors is in this room, but you might have probably seen this formula. So what it states is that if you consider the entanglement entropy of some subsystem of a 2D many-body system, you can often find that the entanglement entropy has this like a leading non-universal term, which is proportional to the area, and there's a sub-leading term, which is a universal data. So we will assume basically the principle of Entanglement Bootstrap, if you may, is to assume that this formula is true, but nothing more than that. So in a way, so you can sort of see why we're calling this as Entanglement Bootstrap. You start with a single assumption, and you basically explore the logical consequences of this assumption. Yeah?
I'm trying to understand the sort of limitations of knowing that the gap leads to area law. So
Right.
What would be the stance in QFT? Because there I would have thought that's sort of somewhat.
Right. So
is that just folklore basically, that we always assume in QFT that if you have a gap, you basically have like an area law in the ground state?
maybe if you have like Lorentz invariants, then this would be true. I can plausibly believe that. I haven't thought about this very seriously, but if you, and this could very well be true, like even for like lattice models. But like the naive argument would be something like the correlation would decay exponentially in gap systems.
Exactly.
So like that would be the argument. But actually, there are like quantum states for which you can sort of concoct. It's not a ground state of local Hamiltonian, which does have like a very small correlation, probably like exponentially decaying the distance, but it actually does not satisfy area law. So you gotta invoke some extra structure. Yeah, so there are these like weird states. Okay. All right. So
Sorry, are there non-counter examples to the strong area law?
there is a counterexample, and I would love to talk about that. So because of I'll just get to that in a few slides actually. But at the very least, even though there are counterexamples, I should point out that this equation has been like studied like pretty intensively in the literature, and at the very least, for a large class of physical systems that we care about, it seems to be a good formula. So that is our starting point. And in this talk, I'll mainly talk about two implications that we have explored so far in this program. And broadly speaking, there are two discoveries that we made over the past few years. So one is this discovery of certain invariants that you can deduce from this assumption. And the other side is computational. And I like to allocate this talk roughly into like half and half into these pieces. Okay, so let's start with that first. So here's some brief comments. So somehow this approach of assuming area law and following the logical consequences seems to be very good at extracting certain ground state topological invariants. By ground state topological invariants, I mean some quantities that you can compute given the ground state wave function. But I should point out that the invariants found out this is like a kind of a like little string that is attached to your product. So invariants found in the Entanglement Bootstrap program may not be an actually honest-to-God topological invariance. And this is because there are the strong area law assumption actually may not be correct in general. So once you find these invariants, like quote-unquote invariants, then you need to actually go into do some extra work to actually show that these are invariants. And oftentimes this is difficult. But nevertheless, I think it seems to lead to many candidates for invariant quantities which have not been discovered before. So at least it seems to be good at generating new ideas. And moreover, importantly, within this program, these quantities can be actually computed. Okay, so then you can go on to maybe use your favorite field theory methods to actually recheck this using your tools. And what's kind of cool is that the result of these calculations, I'm sure, can be like calculated from more conventional methods, but it does not seem to be like trivial from like the go-to like a technology which is like a TQF. So here's one example, which is not particularly interesting, but it is an example. So as I told you, there is this formula for the entanglement entropy, and even this expression for the subleading term is known. But hypothetically, suppose that you don't know the exact expression for this subleading term, and you assume that it is just a constant, okay? Then what you can show is that just from this equation alone, and essentially just the consistency of quantum mechanics, it follows that gamma should have this form. Of course, if you make that little assumptions, it's not even clear what this dA means. So this is supposed to be the total quantum, this entire thing is supposed to be the total quantum dimension. So it's not even clear what the quantum dimension means in this context. But what you can show is that there are these quantities, d sub a, which obeys the formula that they should obey in relation to the dimension of the fusion space, which again satisfies the fusion rules that you are all probably familiar with. So it seems to be like a reasonable thing to call this guy as like a quantum dimension, and this gamma should be exactly of this form. So yes.
I have a question. So from the tensor category axioms, you can show that the dAs are like cyclotomic numbers.
Okay.
Can you also see that from here?
So what I can only say is that there is a formula. So let's say dAdB should be equal to NABC DC sum over C, and these NABCs should satisfy certain like algebraic constraints. So those constraints are satisfied. So, but the cyclotomic part, I don't know. That's all I can say. Okay, so there's nothing like new here, obviously, because this formula was known before that. But when we started to apply this approach to like other more exotic setups, so this is a setup in which the upper side is some topological phase, some gap phase, and on the yellow part you have another gap phase, and between them you have some domain wall, which only has which has a gap, no gapless degrees of freedom, and then you can just like carry out this program pretty mechanically actually, and you find these like new things. So again, this d sub n, these are some versions of quantum dimensions when you have like domain walls, and they are not arbitrary numbers in a sense that they must satisfy certain identities involving these n's, which are supposed to be integers, and you derive this expression for an analog of this topological entanglement entropy in 2D. Yes.
I'm not sure I quite understand what the input to this program is.
Right. So the input to the program is, I think we'll get to that later, actually. Yeah. So There are certain objects, I will say this, there are certain objects which become well-defined under this area law assumption, and those will be the input, but I will define them more explicitly later. In the third example is the following. So imagine you have a 2D gap systems with a let's say chiral edge theory. Then there's the chiral, let's say C minus is the chiral center charge of the edge theory. Then there's a bulk formula that sort of extracts C minus, not just like mod 8 or mod 24, but really honest to God C minus, where this quantity is an expectation value of the certain commutators in the bulk. So you might be thinking like, how is this even possible? Because one might be tempted to think that maybe there's a large emergent symmetry group which is responsible for these formulae. But I'd like to emphasize that really the only assumption that went into this was this strong entanglement area law assumption, which has a priori nothing to do with the symmetry. So, because this is supposed to be an overview talk, I thought it'd be good to like tell you about the basic idea behind how these identities are derived in the first place. And the key technical tool in all of this turns out to be an object called quantum Markov chain. So let's suppose, let's forget about quantum many-body systems. Just imagine you have a tripartite quantum state over Hilbert space A, B, and C. Okay, and we can define it's what we call as conditional mutual information. It's a certain linear combination of entanglement entropies as follows. And quantum Markov chain is a very simple object. If this conditional mutual information is 0, then we say rho ABC is a quantum Markov chain. So that's the definition. Okay. And what's nice about quantum Markov chains, mathematically speaking, is because they obey certain non-trivial identities. For example, rho ABC is equal to that expression, and if you take the log of rho ABC, it can be nicely decomposed into linear combinations of certain log of the smaller reduced density matrices. And you might be thinking that maybe this is because all these objects somehow secretly commute with each other, but I should emphasize that this is not true. So generally speaking, these density matrices do not commute with each other, and you can come with explicit examples, yes.
So is that based on this strong area law?
So this is just a very general statement about tripartite quantum states, but I'll soon tell you why you should expect these states to appear naturally in systems that obey strong area law. This is just a mathematical statement.
Is there some thing to do with locality of the state?
Are you talking about this particular slide
Or that condition that IACB equals 0?
It's hard to say. Maybe I'll go to this slide and it'll become clear for you. Yeah. So one thing that I should emphasize is that if you assume that the strong area law assumption is true, then you should expect for many subsystems, this identity should be true. So why is that? Imagine the size of these subsystems are sufficiently large compared to the correlation lengths so that this identity holds up to a very small error. Then let's look at these individual pieces. So the red one is the leftmost one, A, and the B is in the middle, C is the rightmost one. And if you look at these individual terms, you have AB, BC, and B, and ABC. So let's first think about the area contribution. So, I guess I don't have much to say other than that if you just draw these things explicitly, you'll be able to convince yourself that the area terms actually do cancel out each other. And what about the subleading term? So the subleading term is a constant which is independent, it only depends on the topology of the subsystem. So that should give you minus gamma, plus gamma, plus gamma. So they also cancel out. So it's natural to expect that for these types of linear combinations of entanglement entropies, they should just become 0. And there are specific structures in these 2D gap quantum many bias systems which are inherited from this quantum Markov chain structure. And this program is still going on, so maybe this slide will become different in the future. But so far, like all the identities that we could derive were based on, broadly speaking, two big ideas. So one is, roughly speaking, the locality of entanglement, and the other idea is what we call as the merging. So I'll discuss these individual ideas separately and talk about their applications. So the locality of entanglement. So let's imagine, again, assuming that the individual cells here, their sizes are large compared to the correlation lengths. And suppose you break down your system, suppose this area law, and let's say we choose this region A to be green, region B to be the yellow one, and region C to be the blue one. And by the same argument that I've given you a few slides ago, you can probably convince yourself that the entanglement entropy should satisfy this certain identity. And this implies mathematically that the log of rho ABC should be decomposable into a smaller pieces. In particular, if you look at these like two last terms, log rho BC and log rho B, these are some Hermitian operators that act on this yellow and blue region only. And compared to the size of this whole thing, this is like a fairly local operator. And you can imagine applying this decomposition over and over again. So once you reduce this log rho ABC into smaller pieces, now you just simply declare A to be, again, this green region, B to be the yellow region, and C to the blue region, and again, apply this logic. And this way you can see that, again, this large piece can be decomposed into smaller pieces. And you can repeat this over and over again. Okay, so what does that mean? Yeah.
So intuitively, I might have thought that I could have kind of cut up the system in sizes of roughly the correlation length. Is that what's, because that doesn't enter here. There's no scale set.
So these, so this equation is probably not exactly correct if the system that you're considering is comparable to the correlation length. Probably like only if it's like large compared to the correlation length, it becomes a valid formula.
Good.
So what this means is that if you consider a density matrix of a disk of an infinite system, in an infinite system, that density matrix, if its size is much larger compared to the correlation length, it should be able to we should be able to decompose the log of that density matrix into a linear combination of some local terms. And here I have a quotation mark in local because the individual terms, their size is roughly that of the correlation length, but it's small compared to this like entire disk that you're considering. So there's a well-known formula that if you have a, now we're talking about 2D gap systems with a chiral gapless edge mode, and it is well known that if you have some locally interacting Hamiltonian 2D in the bulk gap, sometimes you can have this protected edge mode. And there's a well-known formula for the energy current. It has this universal form, pi over 12 times C minus times T squared, where T is the temperature. And you can just pretend that this decomposition of the log of the reduced density matrix as some Hamiltonian and plug it into this formula. And there's a well-defined expression for the energy current given any lattice model. So you can compute that, which you would expect, as you would expect, would involve terms that are like supported everywhere. So like there'll be it'll be a sum of local contributions, but that sum will be covered in this entire disk. But there's a pretty remarkable cancellation that simplifies this analysis pretty greatly. And that allows us to say that if you look at any bulk region, which is, let's say over there, and divide up that little disk into 3 pieces, A, B, and C, then the following formula holds. So assuming that this current formula for the energy current is correct, and if you believe that truly this log of the reduced density matrix can be decomposed into these local terms, then it follows that anywhere you compute that quantity, you should always get pi over 3 times c minus. And the reason why you get this kind of simplification is because this assumption that we have these quantum Markov chain structure in these states actually leads to certain non-trivial identities. So roughly speaking, what this means is that the energy current that is associated to the local Hamiltonian, let's say log rho AB, and another local term in the Hamiltonian that's called log rho BC, just vanishes exactly. And because of this cancellation, like majority of the terms just get killed, and you're only left with a few number of terms, and that contribution, by matching to this expression, yields that formula. Okay, so that's like a point that I wanted to emphasize. The fact that you have area law implies that in some sense, there's a locality in this entanglement structure in these gap systems. And now I'm going back to this, going to the question that I received in the beginning. So what is the input to this theory? Because if you think about it, I define these things like dn and n, but where are they actually coming from? So I'm gonna tell you about that in this part. But let me again start with a very general fact about quantum Markov chains. So I've already told you what quantum Markov chain is. You're given a tripartite quantum state, and there's this thing called conditional mutual information. And if that is 0, then this tripartite state is a quantum Markov chain. So that's just a mathematical definition. And I already told you that this implies that you can decompose the log of the Markov chain into smaller, quote unquote, local operators. But there's another aspect of quantum Markov chain which is nice, and it's the fact that you can, in some sense, merge two quantum Markov chains together. So here is again a mathematical fact. So this was due to Kotaro Kato and his collaborators in 2016, and what they showed was the following. So suppose you have two quantum Markov chains. For concreteness, I'll call them as rho and sigma, okay, over ABC and BCD. So they're Markov chains, so so there's a 0 missing here. So I'm saying that conditional mutual information of rho and sigma are equal, but not only that, they must be both equal to 0, because that's the definition of quantum Markov chain, which I forgot to include. And suppose these two density matrices are consistent on their overlapping regions. So one is on ABC, other is on BCD. So they overlap on this region BC. And I'm declaring that they are identical on that region, okay? Then mathematically what you can show is that there is another state on the entire stuff, so not just ABC, not just BCD, but ABCD, such that this state tau is not only consistent with rho and sigma on their respective supports like ABC and BCD, but it's actually a valid quantum mechanical state. And moreover, it satisfies this Markov chain condition again, okay? So this is an important observation that these folks made, which are being used in the Entanglement Bootstrap program over and over again.
Is tau unique or?
Tau is, in this case, tau is unique, but that's because tau is the maximum entropy state that is consistent with rho ABC and sigma BCD. But there may be other non-maximum entropy states which are still consistent with rho ABC and sigma BCD, but they will not satisfy the second condition. So there are two remarks that I like to make. One, as I just said, is that tau is the maximum entropy state compatible with rho ABC and sigma BCD. The second is that tau can be also computed from this fact. So I just declared that this certain linear combination of entanglement entropy should be equal to 0. And okay, so I just wrote that down here. And look at this assumption. So look at this first line. It says tau ABC is equal to rho ABC, and tau BCD is equal to sigma BCD. So if you look at this thing, tau AB that can, well, tau ABC is equal to rho ABC, so this must be equal to rho AB. And this must be equal to sigma BCD, and that must be equal to, let's say, rho B or sigma B. They will be identical. And this is the thing that we don't know, but the important point is that this entropy can be computed from the information about rho and sigma. Okay. What I'm trying to emphasize here is that there are two different ways to compute the entropy. And the important observation in this program is that these two different ways sometimes lead to two different expressions. And that's actually how you derive non-trivial identities in this program. Yeah.
So I don't understand what's the second way? The first way is just using this.
Right. So like, well, they are mathematically equivalent, but the first way is to do this. So you just
define this tau.
well, just plug in like so in place of tau AB, so the thing that you want to compute is S tau ABCD. So you just plug in rho AB here, sigma BCD here, and rho B. And those are the data that is already given to you. So you guys can just, I guess, plug it in your computer or something and just compute this guy. But the first approach is that, well, you're solving this maximization problem. So you have these constraints that tau should be on ABC and BCD should coincide with rho and sigma, but then you maximize this like brute force or directly. Okay. But there is one difficulty, namely this problem of like given some linear constraints, like computing the maximum entropy is actually not a trivial problem. And in general, you really shouldn't expect there to be some like a nice closed form formula. But in our case, in the context of like 2D gaps many body systems, you have enough constraints so that this problem becomes actually tractable. And the way to see that, and now we're getting to the core of like where the input to this theory is coming in, and that's an object that we call as the information convex set. It's some tool that will allow us to define the physical objects that you're more familiar with, such as the superselection sectors and quantum dimensions and fusion spaces. And at the same time, it'll be an object that will allow us to compute this maximum entropy in remark. So it's really the central piece. So now let's move away from this mathematical facts and like come back to the physical world. So you have a 2D gap systems obeying this area. What is an information convex set? Just consider any subsystem. I'm gonna call it as omega. You see that blue region over there. I'm gonna zoom that up. And now I will define a set of density matrices, which are morally a set of states which are locally indistinguishable from this given state. Let's say the ground state, okay? So that is to say, I will look at these like individual constant side balls, which is like order correlation length, and I'll demand that the reduced density matrix that I care about should be like locally indistinguishable to the ground state on these like little patches. So for any ball that touches this omega. So what you do is that so you just enlarge this system a little bit. So you do that, and then you have this set. It's just some set of density matrices. Okay. And what you do is that then you trace out this like little boundary region. So you might think this is a little weird, but I won't have too much time to go into details on why I'm doing this, except instead of just like looking at the set of locally indistinguishable reduced density matrices. But the reason why I'm doing, well, the big reason is that we're trying to get rid of non-universal information. And very roughly speaking, if we don't do this, we will be left with some reduced density matrices which doesn't encode very nice information, and we just want to get rid of that.
So what part are you tracing out? I don't know.
So you started with this like slightly thinner omega, so that's the region that I consider, and I have some. So I will only consider balls of constant size. Let's say like distance 10. Okay, and what I do is that I consider every ball that touches this omega. then I increase the size of omega such that it includes all such balls. So that's omega tilde. So on this thing, I demand that the reduced density matrices are locally indistinguishable from the ground state. But then I remove this region that I expanded back to this original region, omega. So that's this part.
So the size of the convex set will depend on the size of ball you choose.
It turns out, it's not a bad guess, but it turns out the answer is no. It turns out the size of the set, and in fact, not just the size, even the shape of the set, it only depends on the topology of the underlying subsystem. So what I mean by that is that there is a distance preserving linear map from the space of states in here to the space of states over there. And that means that for any subsystem, you can define this information convex set, and they will have these like very specific shapes. So on the top, what I've drawn are like convex sets, like they're all clearly convex, but their shapes are very different. It turns out that the convex sets that we're considering are very specific in the sense that, for example, if you consider a disk, an information convex set of disk, that just has a single element, like a single point. If you consider information convex set of like an annulus, that looks like a simplex. And these individual extreme points, they correspond to the specific superselection sectors. So and if you're somewhere in the middle, that would mean that you have an incoherent mixture of different superselection sectors. And if you have like a disk with two holes, then this will be modulus some assumptions. This will basically form a sphere, like a Hilbert space. So these are all just mathematical facts that, again, as I should emphasize, follows from the area law at the high level. So I just wanted to provide you maybe a too simplistic, but like somewhat non-trivial example on how these calculations will work. So here was the key lemma. I told you that the key point was that given these two quantum Markov chains, you can sort of merge them together to form another Markov chain. And we could compute the maximum entropy by either maximizing the entropy directly or decomposing the global entropy into local entropy, so to speak. Okay, and I told you that this maximization problem is in general not easy, but now that we know what these information convex sets, we can actually do this calculation very explicitly. So here's an example. Imagine you have an annulus, and I have divided that system up into 4 pieces. So you have A and B is a union of those two little disks. C is also a union of those two little disks, and there you have it. And now we have two things. So what we're going to do is that we're going to merge two density matrices, one in the information convex set of ABC, and the other in the information convex over BCB. How does that work? Here's the first approach. We're just going to use this simple formula. So, and what we realize is that first of all, ABC and BCD are both disks. And if you remember what I told you a few slides ago, on the disk, the information convex set has a unique element. And obviously, the global, let's say, ground state should, the reduced density matrix of that into ABC and BCD should be an element of the information convex set. And therefore, this rho ABC and lambda BCD, whatever they are, they should be exactly equal to the reduced density matrix of the ground state. Let's call it as sigma. So you just plug that in, and then you get this formula. Okay. The maximum entropy is equal to this quantity, which only depends on the ground state entanglement. But that part is not too special. But there's a second approach, which is to directly compute this carry out this maximization problem. So how does that work? Now you realize that the information convex set of ABCD is actually a simplex. So I think I've already told you that. And that means that without loss of generality, you can write down this density matrix tau ABCD as a convex combination of certain states. So this here PA is some probability distribution, and rho A, each of them are representing specific superselection sectors. In particular, that means that each of these rho A's, they must be orthogonal to each other. And that means that if you plug in the expression, plug this tau into the expression for the von Neumann entropy, you get this nice formula. There's an entropy contribution coming from this like P of A, and then you have like the average entropy contribution over these like individual extremes. And the only variable here is this probability distribution like P of N. And if you look at this formula, the first part looks like entropy of some like StatMech model, and the second part looks like the energy of some StatMech model. And of course, this maximization problem becomes like a minimization problem of some free energy of the StatMech model. And we all know how to solve that problem. The solution is given by the Gibbs state. So you just plug that in, and what you're gonna get is this formula. I took the liberty and rearranged certain terms so that things look a little bit nicer down the road. But here's the formula. So in essence, we have two formulae. One, yes.
This sigma ABCD is the ground state of the system.
That is from the ground state, yeah.
And this tau would be something that's not the ground state, but
Right,
also
exactly.
has some area law.
Right, exactly. Yeah.
You want to also find the ground state of the system, no? Or are you imagining you always know the ground state?
So in my mind, the ground state is already given to me,
Okay.
and that's some state that obeys the area law.
Okay.
Yeah. And the sigma, if you look at this, the sigma actually cancel out each other. So I just put it in there because in the expression that I'm going to write down here, it'll become it'll become clear why I did that. Okay, so I will just declare. So this quantities like this individual terms, it's some quantity that depends on the individual superselection sectors. I will relate this to what you know as like quantum dimension, and I will justify it shortly. But for now, I'll just call this as like dn. Okay, it's just it's a definition, which I will later justify. And then you see that on the left-hand side, what you have is a linear combination of entanglement entropy that involves just ground states. So sigma was the ground state. And the right-hand side, you have this object, okay? And if you consider one of the partitions studied in that paper, you would probably recognize that this shape looks very similar to that partition. In fact, it's exactly equal to that. And there, what you can see is that this thing is actually equal to the total quantum dimension square. But of course, you might ask, okay, so like here, am I just playing tricks here because I just simply declare that this is this as like the event, and maybe these are not like actual quantum dimensions. Maybe I just like redefined everything. But what we can also show by essentially applying the same trick for this setup. So you have instead of merging two disks into an annulus, you have two annulus over ABC and BCD, so that you merge them together and you get a disk with two holes with a specific supersolution sectors A. If you essentially do the same thing, you get a formula like this, where NABC is a Hilbert space dimension of the dimension of a sum Hilbert space. Yeah.
How did you pick rho n? Is that basis undefined or anything?
So it's not like we picked them. So what you can show is that the information convex set is always of this form. So any element of that set must be a sum, like a convex combination of orthogonal quantum states.
Saying there exists a unique set of rho n.
Yes, absolutely. And of course, depending on the state, depending on the actual underlying state, this set will be different, obviously. And those are the really, like, quote unquote, the input to this theory. But those inputs are like actually hidden in the ground state, these like fusion space dimensions and quantum dimensions. Because this entire procedure of like maximizing the entropy and finding a set of like locally indistinguishable states, these are all like some things that you can explicitly do on your computer. So in principle, you should be able to find all of these sectors and their fusion space dimensions from the ground state. Okay, so anyway, the point is these that I defined in the previous slide actually satisfies this constraint. And moreover, these NABCs, these dimensions of some chemical spaces, actually obey the fusion rule. So that's how we justify that these are actual like quantum dimensions. But the key point of this program isn't that you can just reproduce like old well-known results. It's that there are actually identities which seem new. So I won't have time to discuss like what this identity means, but the point is, if we extend this to like more exotic physical setups like 3D gap systems or like 2D systems with a gapped domain wall between them, you seem to get new relations that we were unaware of. So I like to draw some analogy between the Conformal Bootstrap program and our program. Of course, these are completely different programs, but I think there are some nice parallels. So here we have a physical axiom, which is the area law, which may not be always true, but it's an assumption. And the objects or quantities that we care about are, instead of being correlation functions, these are density matrices over different subsystems. And the fundamental data, like the analog of the scaling dimensions or peak coefficients, would be like the information convex sets and the extreme points in that set, because they obey certain very nice specific constraints. And those constraints can be essentially all derived from this like a merging identity. So for the case of the 2D system, there's a nice correspondence between the objects that are defined in the Entanglement Bootstrap program and some more familiar data, and also the identities. And I decided to not talk about like the new results. So I'm here during the afternoon. So if you want to chat about this, like I would be happy to do that. But as I said before, it looks like we're getting new super selection sectors that we weren't aware of before, and the identities that the fusion space dimensions and the quantum dimensions of these sectors must satisfy, both in the case of 2D domain wall and also in this 3D system. Okay, so now I want to switch gears a little bit and also take a little bit on the computational side. So now the big goal here is to, given a locally interacting Hamiltonian that you can write down, we'd like to maybe calculate this ground state energy or ground state wave function very accurately. And to this end, I'll briefly sketch about the problem that may seem totally unrelated to what we have been talking so far, but I can assure you that it is related, and this is called as the marginal problem. So I will first start with the classical version of this problem. So usually if you go to like undergrad like probability courses, you'll be given a probability distribution over two random variables x, y, and you would sum over random variable x, and you would get a marginal probability over y. But here the problem is different. What is given to you are the marginal probability distributions, and what you're asked is if there are some global probability distributions that is compatible with this marginal probability distributions. If you think about it, there's a very natural quantum generalization of this problem, which is known as the quantum marginal problem. And what is given to you are marginal density matrices, and you want to understand if there's some global density matrix compatible with these things. So the reason why I care about this is because if you can solve this quantum marginal problem, that would immediately lead to an efficient way to compute the ground state energy and ground state correlators in general. Because you can formally write down the expression for the ground state energy as the minimization problem of the energy with respect to density matrices. But then you realize that oftentimes the individual terms in the Hamiltonian only act on like constant number of sites or something. So for that expectation value, you can only, when it comes down to computing that expectation value, it suffices to know only the reduced density matrices on these individual regions. So if you can somehow like solve this minimization problem with respect to this constraint that these marginals are consistent with some global state, then it looks like maybe you can reduce this exponential cost down to a polynomial cost in the system size. But of course, that doesn't quite work because if it was that simple, like somebody would have done it and we wouldn't have to like invent these like new like nice tensor networks. Yes.
But isn't this ground state problem QMA complete?
Yeah. So this as I said, like this is not going to work. Yes. Yeah. But I'm just trying to motivate this. Yeah. The real question is like, can you actually efficiently check that these are consistent? So that's the real problem. And this problem is like not new. It was like already mentioned by this guy, Coulson. He's like an old school quantum chemist from the 1950s. And like people already knew that if you can somehow find this like consistency conditions for these like local correlators, that will allow us to, you know, compute many physical quantities of interest very efficiently. So usually for this problem, like showing that it's something is impossible is easy. So for example, I've shown you this like conditional information. So that thing is supposed to be non-negative for any quantum state. So if you have some like marginal density matrices such that it violates this condition, if its conditional information is less than 0, then clearly that can't be like compatible with any like global quantum state. So like coming up with these like constraints that needs to be satisfied, like the necessary conditions, that has been there are some progress. But the difficult part lies in like showing that for real there is a global density matrix that is compatible with these local density matrices. So that has been very hard, as just mentioned. In fact, the general version of this problem is QMA hard. What that means is that it's basically like a quantum version of NP, so like much harder. And yes, it's sort of a joke, but it's a true story. So this senior mathematical physicist once told me that basically people disappear after working on this problem, and they make the same mistake. But there has been some like special conditions. So obviously, the way to think about these like QMA or NP, like if you're a physicist, is that it means that there shouldn't be any like a general purpose algorithm that solves this problem. But it doesn't exclude you from like coming up with like special purpose algorithms. So there is a logical possibility that maybe there are some special conditions, which is only applicable to a certain subset of physical systems, such that you can actually guarantee the existence of a global state. And this strong area law assumption, it turns out that that's actually that condition. Okay, so what you can show is that imagine you cover up your like entire system into like small like overlapping patches, and what you demand is that within each patch, this is satisfied. And okay, this is checking this assumption is like kind of complicated, I admit that, but you're considering a finite patch. So in principle, there's like a finite number of conditions that you need to like verify. And the second condition is that when you have like two density matrices on like two patches that overlap with each other, on the overlapping region, they should be like consistent. So that's what I mean by locally consistent. But if you think about it, this is like, obviously this is necessary because if these local things are incompatible right there, there's no way there's like a globally like consistent thing that is compatible everywhere. But also more importantly, this condition can be checked like easily because these are like both of these things are like finite dimensional matrices. So you can just write a computer program to check that this is correct. So yeah, so why is that? Sorry, I realize that I'm running out of time, but just to be clear, this condition. So I told you that if every marginal satisfies this condition and the second condition is satisfied, then we know that there's a global state. like more concretely, what I mean is that like if you like divide up your system into like little say like lattice of this form, and if you consider like reduced density matrices over like 3x3 subsystems, okay, and compute these entanglement entropies, and if they satisfy this constraint, then we're good. And what these constraints mean is that if you, for example, see this like gray square, that means that you're taking a partial trace over these gray squares. So like for instance, like this guy, I'm after tracing out these gray things, we're left with like 2 squares here. And what this just means is that the linear combination of the entanglement entropies here should satisfy this identity for every local patches. And the key point is that if you believe that this area law assumption is true, then you can very easily show that these conditions are satisfied. Okay, so that's what I just told you. And I won't have time to tell you like the exact argument behind this, but I will tell you one thing, which I hope can convince you that this is not totally implausible. So I already told you about this like merging idea by Kato and his collaborators. And so far we focused on the maximization aspect of the entropy. So the point was that there are 2 different ways to compute the entropy, and we were able to derive non-trivial identities by computing it in 2 different ways. The aspect that I want to focus on now is the following. So here, if you look at the second line, what you see is that tau is again a quantum Markov chain. So you started with 2 Markov chains, rho ABC and sigma BCD, and you somehow combine them together into this like sausage factory, and out comes another Markov chain over this larger region, ABCD. So roughly what's going on here is that you start with like these like little Markov chains that are spread like throughout this 2D lattice, and locally you can use this recipe to combine them into larger Markov chains. And you just keep on doing that until you can't. And apparently, actually you can fill the entire lattice this way. So like here's like a diagrammatic like representation of what I just showed you. You start with 2 Markov chain states. So you have BCD, ABC, and they satisfy this Markov chain condition, and you can combine them together into this larger piece. And you can actually do this for like 1D system. This part is like not like too crazy to think. But if you believe that this argument works for 1D, you can probably also believe that some version of this argument works for 2D if you are given a Markov chain over these like long like slabs. And a highly non-trivial fact is that the existence of these states on these slabs actually follow from this like a local Markov chain conditions. I won't have time to discuss why that's true. Okay, so yeah, so where do I see this thing going? So it looks like what I find personally surprising is that you start with so little, but you seem to get these like pretty non-trivial statements. And to me, that's pretty surprising. And as I said, it's not like this thing is perfect. So the strong aerial assumption is kind of a strong assumption, but at the very least, it seems to be producing new like candidates for like a ground state topological invariance. So it'd be fun to like think about how to compute or like actually reversely show that they're like a true honest to God topological invariance. And I think the problem of coming up with numerical method that solves like interacting like lattice models, like efficiently on a classical computer, that's an important problem. And we don't know how well this will work, but well, it's a new approach, so I think it's worth thinking about. And the big, I guess, slogan for me is that this quantum Markov chain states, it's everywhere in these like gap systems, and they seem to be like little Lego blocks which are very intricate that you can like recombine together. Okay, so that's it. Thanks a lot.
Yeah, Yeah, for topological phase, you usually form a group structure. You can stack two different phase and condense some boson. So from your approach, you calculate some many topological invariant. Can you recover this mathematical structure when you stack this phase with this invariant, with the other phase with other invariants? What is the outcome of the stacking phase?
Right, so let's see, so they are, so the question is like, basically, are they additive or something? So, okay, well, let's see. Everything that we consider, I think they are additive under stacking, actually. So yeah, but you know, there's sometimes these like Z8 invariants or something, so those things I don't know how to deal with.
But so can you also get things that involve moving anions around each other, like
Right, so
grading
actually,
statistics or-
yeah, so one of my collaborators, Bo and Shi, he did a lot of work on that. So you can actually define things like S matrices, for example.
And you can get Verlander formula.
Yeah, you get it, yes, yeah. So,
And also FNR, so everything you can get from.
so the thing is, so we haven't seriously thought about getting F symbols. Last time we discussed, I think it's not totally unreasonable, but that's technically speaking not done yet.
F symbols like 3J.
6J.
Is there some physical meaning to the new topological invariants?
Oh, let's see. Right, good question. So,
Could you repeat the question?
Is there some physical meaning to the new topological invariants?
right, so, oh yeah, so there is one thing that I find really cool, actually. There's this. Yeah, this thing. So, so that thing. It turns out that if you have a state which can be written down in a suppose you have a real wave function in some local product basis. So what I mean by that is the little wave function is a sum of like AI, like state I, where individual AI is all real. Then you can show that this thing is zero, like this quantum mechanically. So what I mean, I guess maybe it's not too surprising, but what this means is that if C minus is non-zero, if it's so if the wave function is real, then C minus should be zero. And in particular, if C minus is non-zero, then there should be some intrinsic sign problem. So no like a local unitary should be able to remove that. So that's, I don't know, like one physical meaning. The other ones, I think it's less clear.
Okay, because I thought you had some like new topological invariants that.
Oh, I see. Oh,
yeah.
those things. Right. Okay. I see. Yeah, different question. So, yeah. So this thing, well, what can I say? So this DN here is basically like quantum. So there are sectors that you can define which are sort of associated to the like a half loop. So like when you have domain walls, you can sometimes like measure the topological charge as like localized on the domain wall by instead of doing the whole like an Marginal Problem experiment on the loop, just doing on a half loop. And these are the quantum dimensions of those guys. And these corresponds to, I guess roughly speaking, the fusion spaces of those guys.
So this quantum marginal problem you mentioned reminded me of some work that was done that basically took like a linear functional approach to like putting bounds on just a generic quantum many-body system.
Right, yeah.
So like, do you think that just basically assuming unitarity, you could with something like that, could you combine this with that?
Yeah, so I do think about these things a lot, but I'm afraid I don't have anything concrete to say. But what I will say is that our constraint is nonlinear, so it seems very difficult to like recast into like a finite set of like linear constraints. Having said that, like when I talk to different people, like some people suggested that maybe you would just impose these linear constraints, and then as a final step, you would somehow like quote unquote round that into the density matrix that obeys this constraint. So that part, I don't know how to do it, but that's like natural, that's like one thing that is natural to think about. I don't know, I don't have any concrete things to say in this direction. First, yeah.
Do you think it's easy to impose some symmetry constraint? Because on the 2D topological order, if we enrich by symmetry, it's like a G-cross category is quite a complicated object. So do we expect to observe this kind of topological invariant for this?
Right. So I don't know actually. So the main thing is that, well, actually in this framework, to me it's not even clear how you would see like SPT actually, because it's like kind of too coarse. So I don't know, but maybe some kind of like more refined entanglement measure might be helpful.
So for the quantum marginal problem, does that like assuming your state is like area law, say, if I specify like the density matrix on patches which cover the whole thing, that's like sufficient to recover the original.
Yeah. So it suffices to have area law locally, and that implies like not globally. So yeah, here are the logical relations. So if you assume strong area law holds locally, that implies that it holds globally as well. So that's mathematically correct fact. And also, independent of that, if area law holds locally, then the consistency problem is also solved. But it's not like you start from it's not like you're assuming that the area law holds like everywhere at a large scale, and then from that that there's a consistent global state.
So it's enough for if I want to specify like a global state, it's enough to assume, or it's enough to specify local density matrices and area law.
Yeah, that would define a global state.
Okay, and is there any constraint that would make it like pure or?
Oh yeah, so well, okay, so I did some numerics for like toy versions of this, and I guess what I would do is that I would minimize the energy subject to this like nonlinear constraint, which is like hard to enforce. So I would add like a Lagrangian multiplier and just do the constraint minimization problem. I guess that's the only way that I could think of at the moment. I don't know how to like just enforce this condition like right from the beginning. So like I don't know a nice parameterization of the density matrices that obeys this constraint.
In your numerical approach, in one dimension, what does it reduce to, or is there anything
Right.
to
So
say about it?
in one dimension, better to show a picture. Let's see. Yeah. So it reduces to a like matrix product operator, but a somewhat special matrix product operator in a sense that you can compute the global entropy. So so the state, so these local conditions imply some existence of some global state compatible with this guy, and that is it's like a finite bond dimension matrix product operator essentially.
I think I'm just some sort of key ingredient in the bootstrapping the ground state. So
right.
What I understood is if you have the strong area law, and I knew the local or the marginals, then I can reconstruct the global state.
Yeah.
But so if you're trying to bootstrap, I give you some like mini body Hamiltonian,
right,
and you want to tell me what the ground state is.
Right, yeah.
What do I guess? I make some sort of ansatz for the local.
Oh yeah. So you like
there's no constraint on those, or are there?
Right. So like if I just like minimize the energy subject to like the local consistencies, like that will not give you a variation upper bound to the ground state, because there's no guarantee that there's a global state compatible with these like local marginals. So in that case, what you would get is actually a lower bound to the ground state energy. So what I would personally do is that I would like increase the patch size, and for each patch size, I'll just as an increase, I would just demand more constraints from this like entropy.
So the constraint is just minimizing the energy.
Minimize the energy subject to this nonlinear constraint of this local Markov chain condition.
Great, so that's
That will provide a like variational upper bound to the ground state energy.
In 1D, does bootstrapping lead to the same results by like Hastings and?
Let's see. So I actually thought about this. Let's see. So let's see. In a way, yes, but that's a non-trivial fact. So at a high level, what happens is that this bootstrap condition in 1D, it implies that you get a there exists a global state which with like decay of correlation. And what people have shown was that in 1D, if you have like exponential decay of correlation, then there exists a matrix product state. Like if you have like a 2-point function exponential decay of correlation, then you can show that like more stronger form of like decay of correlation applies. And that implies that there's a matrix product state which approximates this entire thing with a small bond dimension. It's actually a very, very non-trivial fact.
okay. If there are no more questions for the speaker, let's thank him again.
So easy.